We're going to work through the quantitative material from the Letter to My Son activity, which covers ratios, percent change, and the rule of 70. There's information on the actual assignment, but we're going to talk through it, make sure it makes sense, and work through some of the examples that are included there. Let's start by looking at the assignment and starting with ratios. We'll see what we've got. The ratio is a way of comparing numbers. So it is the way of comparing that sounds like something is double or something is 4 times as many. That's like what a ratio tells us. If we say a ratio, we say it as 2 to 1 or 5 to 2 or something like that. The number on the bottom does not have to be a 1, but it often is. Saying something is double is like saying it's a ratio of 2 to 1. For every 1 I have of one thing, I have 2 of the other. Okay. So the example here, we talk about pi, but then the example that we work through is about distance. And so this tells us that the distance from the Earth to the moon is about 250,000 miles at its maximum. And the distance from New York to LA is about 2,500 miles. We have this worked out here, so we can go ahead and actually work through that on our own and make sure that it makes sense. So I'm going to start with those distances. We were given that the distance from Earth to the moon is about 250,000 miles. Most of the time, an approximate ratio or a ratio of approximate numbers is good enough. Sometimes we'll need exact numbers, but in this case, we have approximate numbers. The distance from New York to LA is 2,500 miles. Okay. One thing that's important to note is that these are in the same unit. If one of these were in miles and one were in kilometers or yards, we would want to make sure that we put them in the same unit so that we can compare them meaningfully. To set up our ratio, it asked us for the ratio of the distance from Earth to Mars to the moon, be a little further, to the distance from New York to LA. And so we want to start with putting those distances in. Oops, but there we go. 1,000 miles and 2,500 miles. First thing we can see here is that both the unit on top and the unit on the bottom are miles. As I said, those need to be the same. A great thing happens there then because those cancel out. Like we saw in unit conversions, the same unit on the top and bottom divide to equal 1 or to cancel out. So we don't have a unit, and that actually is correct for ratios. Ratios don't have a unit. Now we just have the numbers to deal with. Since these numbers are very similar looking, they're easy to work with. You can divide these using a calculator or with pencil and paper if you want to or if you need to, but we can also use a shortcut on these because I can see that you can divide each of these by 100 and quickly cancel the 2 zeros on the end. That leaves 2,500 over 25. Because this 25 is the same in both places, I can cancel it and reduce it to a 1. That leaves me with 100 on top and 1 on the bottom, telling me that the ratio of the distance from Earth to the moon compared to the distance from New York to LA is 100 to 1. It's another way of saying it's 100 times farther from Earth to the moon than from New York to LA. If you think about that, what that would mean is that you could take 100 trips from New York to LA, and that's the same distance as taking 1 trip from Earth to the moon. You can write a ratio a few different ways. A very common way that we see them is like we have here is a fraction. But we also can write them using a colon, 100 to 1, or we can actually use the word 2, 100 to 1. So depending on if we're writing about those or if we're reporting them just in a homework problem, you might see these in different ways, and they're all correct. It it is important that we have the 2-1 here on the back of the colon or the word 2. If we just said the ratio is 100, that's not quite correct because a ratio is comparing two things. We need a ratio of something to something else. We need to have both parts. It means the same as saying it's 100 times, but we need to have all of this to be the ratio. So we can look at our document and see that that is in fact what we have here. These distances are filled in and we have a ratio of 100 to 1. That's good because that's what we just went through. And there's a way of saying it as well here that should match what I just said. So let's move on to percent change. Another way of comparing numbers is to talk about a percent change or percent difference. We use this often when we're talking about an increase or a decrease. And so we might have a number that on like temperature at some time of day versus temperature later in the day, or on one day versus another day. Another really common one, which is what one of our examples is here, is about stock. And so we can have a value at one point in time and compare that to a value at another point in time. And we want to know how much it's increased. Rather than finding out the actual absolute difference, which we would get by subtracting, we want a percent difference, okay? So we're gonna work through this example we did a second ago, and we will make sure we get the same thing and know how to interpret it. Let's clear this off. All right, let me get my numbers. We know in the problem it says that the percent change in the value of the S&P 500 during President Obama's first year in office is a change from 805.22 in, that's in 2009, so that's like our starting value. And then we have a 2010 value 1 year later. That's our ending value, our new value. And that one is 1150.23. And so we are going to plug these into the percent change formula, which is given in the example when it's worked out in your packet or in your handout, but I'll put it here as well. We want to compare over time. Almost always, there's probably an exception somewhere, but almost always, we want to take our new value and subtract our old value and then divide that by the old value, okay? At the end, we're going to want to make it a percent, so we'll need to multiply by 100. Why do we do this part? Well, taking the new and subtracting the old from it gives us what? That tells us the actual amount of the raw change. So that is actually the absolute difference in the numbers, just subtracting them. So if we went from a GPA, for example, if we went from a GPA of 3 to a GPA of 4, that would be a 1 GPA point increase, which would be really big, which would be great. But that means that I increased by 1. So a positive value, if I go up over time, that would give me a positive value because I increased. If I subtracted these in the other order, if I did old minus new, I would have 3 minus 4. And that would give me a negative value. And that would sound like I got lower. That doesn't make sense there. So we definitely want to have the new minus the old, okay, in most cases, including this one. So what value are we at? 1150.23. And that's an increase from 805.22, okay? All right, that, when I plug it in here, either, again, you can use a calculator or do this by hand, and I will do that in a minute, but we have to figure out the other part of the equation as well. The point of the top, as I said, if the subtraction is to figure out how much actual change there is, what is the point of dividing by the old value? Well, that gives that amount of change a little bit of reference for us. It puts it into perspective. So thinking again about the GPA scale, if I increase 1 point from 3 to 4, it's not a very big increase or a very small increase. Well, how would I know that? Well, what was my starting value? 3. So I went from 3 to 4. I increased 1 point from a starting point of 3. So if I take that and I do this formula, I get a 33% increase. That's a 1/3 increase. I did 1/3 better. A whole third of my original value improvement. That's really big. If I had a test score where I went from 78 to 79, that also is a 1 point increase. Is that very big? Well, let's think about that. That's 1 point increase on a starting value of 78. So that's 1/78th an increase instead of 1/3. So that's actually very small. So both are 1 point increases, but because we start at such different values, because they're on such different scales, one is really big and one is really small. So the dividing tells us, is this a big difference or a small difference? How big is this change relative to where I'm at? But it is an important piece that we add on versus just subtracting. So in this case, my old value is that 805. That was my starting one, the 2009 value. Here we go. Okay. Then I need to just calculate this part. When I calculate the numerator, I can subtract those and I get 345.01. And when I then divide that by 805.22, write that in again, 22, I get 0.428, my decimal better to see, and lots of other numbers after that, but that's approximately what it is. And so if I look at that, that's a decimal. It's not a 0.428% increase. This number is a proportion. Proportion is the decimal version of a percent. I have not yet made it a percent. That's the purpose of this times 100 bit. So move the decimal place over, multiply by 100, and I get 42.8%. For me, 1 decimal place or 2, no more than 3 probably, is fine. In different classes, there will be different rules, but generally using a reasonable number of decimal places is going to be okay. Sometimes an assignment will tell you exactly how many to use. Otherwise, just use your good judgment. So that tells me 42.8 increase. So what does that mean? That means that from January of 2009 to January of 2010, the S&P 500 value rose 42.8%. That's almost half. It almost rose by 50%. Half of its value on top of itself. That's seems like a pretty big increase, percent increase. It is positive because it was an increase. If it had gone down, that's okay, that happens too. Then this numerator would have been negative, which would have carried a negative through and given us a negative percent. A negative percent change means a decrease. So that would have told us that the value of the S&P 500 had decreased by whatever percentage over that year. In this case, we have an increase. So we want to make sure we're a percentage. We want to make sure we've got the correct either increase or decrease, and then make sure that value seems reasonable. It's a good way to catch calculation mistakes. Okay, so let's flip back to the assignment again and check 42.85. So here we would put 2 decimal places. In the example I just did, I only brought 1. Either is fine here. And then there is an example from a later time, from a later set of years where the numbers are here. And you can do those on your own and make sure you get an answer that is reasonable. Check if it's an increase or a decrease, and should it be, and check that your value makes sense. Okay, So that's ratios and percent change. Now we're going to talk, the last thing here is about the rule of 70. So this is about compound growth. Compound growth is what we're talking about with like interest rates. It can be on loans or on accounts, savings accounts or CDs, things like that. And there are formulas, you have probably used them before, about how to calculate compound growth. They can be, they're kind of complicated. They're not very easy to do in your head, certainly, or with quick paper and pencil math. So there is a rule of thumb that is called the rule of 70. And it gives us a quick way to think about how compound growth is happening specifically with one thing, which is doubling. So where the more complicated compound growth formulas, it's not about doubling necessarily. You can use any increase you're interested in. But this is using an interest rate to calculate how long it will take to double, okay? So you can see the rule here. You can read all of this, but this little middle paragraph I'm gonna look at, it says, if a variable is growing at a compounded annual growth rate of X%, so that's something that you would probably be given per year, it doubles in size every 70 divided by X years, X being that percent. So you just take 70, divide it by whatever the percent growth is, and that tells you the number of years that the money in that account will, if it's money in an account, that it will double. Another time, besides money in account that we use this is with population. In that case, the population would double every, so often it could be population of bacteria, it can be population of a country, it, like I said, is often money. So let's look at our examples here. What this shows in this last paragraph here is talking about not a specific example, but just why a percent more makes a big difference. And they're saying that if it grows at 1%, it will double, the value will double in 70 years. But if it even could grow at 2%, it will only take 35 years to double, okay? So we'll look at those numbers and then see about another example. Let's see. All right, so that formula is an easy one, 70 divided by X, X being the percent growth. And I want to point one thing out here. Almost always when we calculate with percents in formulas, we use the decimal version. We actually use a proportion. So if you want to calculate a 25% discount off of something, you multiply the value of the thing by 0.25, not by 25. It would get bigger in that case. But in this formula, we actually use, in that case, the 25. We use the number itself, the whole number, not the proportion version. So that's a difference. So in the example in the problem, where we're comparing the doubling time difference from 1% to 2%, what happens? We actually have an X value of equal to 1 in this case. So we would say, well, 70 over 1, that's easy math, that's 70. Remember our units on this are years. Okay, put a Y here. 70 years, what does that mean? That means that however much money I put in at this 1% growth per year, my money will double in 70 years. So if I put an account in when I was 10 years old and I put $1,000 in, it grows at 1%, then by the time I started at age 10, by the time I'm 80, I'm gonna have $2,000. So that is kind of slow. If I could get at least that rate to double to 2%, then 70 over 2 gives me 35 years. Now, in that case, I would have, it's in the same situation, I would have $2,000 by the time I was 45 instead of 80. So it cuts the time in half is a way of thinking about that it takes to double, okay? And this continues to go on if we went up to 3 or 4 or 10 or whatever. So let's do an example with it. Let's say that we know an amount, let's see, we're working with $5,000, and it's going into an account that makes 3%. So these are, it's not going to work out quite as nice for numbers as these did. And I want to know maybe a couple things. Maybe first I want to know how long it will take to double. And maybe I want to know something like how many years it will take, like when will it reach a certain value, like $15,000. Or I could say, well, what will the value be in 20 years or something like that. So let's get into this example and explore it a little bit. I use my formula. My x is 3. Okay, so this is where I didn't pick a nice one that worked out. 70 over 3 is 23 1/3 years, or 23 years and 4 months would be a way to think about that. That might make more sense with time. So that means, so how often will my money double? How long will it take for my 5,000 to turn into 10,000? 23 years and 4 months, 23 1/3 years. That's how long. Okay. So if I wanted to know something, so then I'd have 10,000, which would mean in another 23 1/3 years, I would have 20,000. So if I wanted to know, well, how much will I have at a certain point? I could say, well, this is in 23 1/3 years, my money doubles, which means I have $10,000. Okay, my amount. And then it still keeps going at this rate. It would double again in another 23 1/3 years. So let's say another 23 1/3 years go by. So now it's been 46 years and 8 months. How much will I have? Well, it doubles. Not the 5 doubling, now the 10 is doubling. I have 10. So in another 23 years, now I have $20,000. Okay. If I can hang on another 23 1/3 years, so it will have doubled 3 times. It will go to 10, to 20, and then to 40. I'll have $40,000 in, well, that's 70 years, 3 of them. In 70 years, I'll have $40,000. So again, if I did this when I was 10 years old, by the time I'm 80, here, if I put $5,000 in at 3%, I would have $40,000. Okay. That's kind of how this works. We can get a dollar amount at a certain time. We can figure out the number of years to double, and it really works best for approximate numbers. So if I cared exactly about how much I would have at 20 years, it would take a little bit more work to find that out. But if I wanted to know approximately how much I would have, I could estimate that. I could say, well, not 20 years, but in 23 years, it'd be $10,000. Okay. We can also compare with this resource like we did with this formula, like we did at the beginning, where we can say, well, hey, if you have 1%, here's what happens. Here's how often it doubles. If you can get to 2%, doubles in half the time. So we can compare different situations as well. I hope that makes sense. Let's go ahead and make sure that we've covered everything. So you'll get into your applied problems, and they should all be doable based on what we just went through. Of course, if you have questions, please see me or any of the peer consultants in the quantitative studio. You can make an appointment or send me an email, and we'll be happy to help you. Thanks.